All right. So we'll proceed now. So we have established before that this is an exact differential equation. So the idea is that we're suggesting this is obtained, or this was obtained from the total differential of some function f of x comma y. So its second partial derivatives, the mean second partial derivative, should be the same. So if that is the case, when I differentiate this coefficient of the x with respect to y, it should give me the same result as differentiating this coefficient of the y with respect to x, and we've established that before. So we said that this one will usually be denoted as m of x comma y, that's x coming first before y, the same way m comes before n, and then we say we denote this one as n of x comma y. So for us to establish that it's an exact differential, we said that del m of x comma y del y should be equal to del n of x comma y del x. So in this case, this is going to give us what? So our m of x comma y, as we have identified above, is 2xy. And of course, when we differentiate this with respect, partially with respect to y, we're going to have del m of x comma y del y to be equal to, that means in this case we are keeping our y as constant. Sorry, we are keeping x as constant, we are differentiating with respect to y, so that's going to give us this 2x, because x is a constant, 2 is a constant. Okay, so then we differentiate this del n del x. So don't forget that the n of x comma y is equal to 1 plus x squared. So when you differentiate this, you're going to have del m del x should be equal to, sorry, del n in this case of x comma y del x. When you differentiate with respect to x, this is going to give you 2x. Okay, so it's obvious that they are equal, so we can identify that since del m of x comma y del y is equal to del n of x comma y del x, we say that what the equation is exact, the DE is exact. Okay, so that is that about it being exact. Then we are told that if it's exact, we should solve the differential equation. To solve this differential equation means that we should obtain that function f which depends on x comma y, which will define y implicitly as a function of x. So you are going to have an implicit function as a solution to this exact differential equation. So to find that, we'll simply use the idea that if this, since this is exact, this is going to be the derivative, this m of x comma y is going to be the derivative, partial derivative of that particular implicit function f with respect to x, and this is going to be the derivative of that implicit function partially with respect to y. So we can start off with any of them. So in this case, we're suggesting that, so we now say that let f of x comma y, oh, let me just that, okay, so in this case we are suggesting that our f of x comma y is a function sorry, please let me adjust this. So that solution is f of x comma y. So let's say be the solution, okay, such that in this case our del f of x comma y del x, that's the coefficient here of the x. If this is a total differential, as we have established now, that is an exact differential. So that means del f of x comma y del f is equal to del x is equal to 2xy, and del f of x comma y del y. That's going to be our coefficient of dy here, which is 1 plus x squared. So from here we can integrate this, let's say some partial integration in that case. So you can take either of them, you can start with either of them, but so the idea is that from here we can get del f, okay, del x to be equal to 2xy, and from this we can get our del f to be equal to 2xy del x. Then we can integrate both sides. So don't forget we're integrating with respect to x, we're keeping y as a constant. So in this case we're going to have this to be f is equal to, this is going to now give us 2y, because we are keeping y as a constant, integral of x del x. Then from here we have f to be equal to 2y, then this is x squared over 2 plus, so normally when you integrate you should have some constant of integration, but in this case you are integrating partially with respect to y, so you would not have exactly a constant. You're going to have a function that depends only on y. So what's the idea behind this? It's the fact that if I have a function, let's say I have a function f to be equal to 2x, let's say it's equal to x squared plus y, or let's say, yeah, x squared plus y. By the time, or this can actually be y plus 5 or sine y, everything just depending only on y, everything you have left here just depending only on y. And then when you differentiate this partially with respect to x, that means you are keeping the other portion constant. So at the end of the day, you're going to have 2x when you differentiate partially with respect to x, and every other thing here will have its derivative to become 0. So if I want to get this original function back from this by integration, when I integrate this, of course I'm going to get x squared. I know that what I have left will be a function that depends only on y, because that would have had its derivative to become 0 when I was doing this partial differentiation with respect to x. So that is why we now say, okay, this will be some function of y instead of having it to be just a constant. Okay, so this is quite different from a situation where I have f, or I have something like just f of x, and then by the time I differentiate, I'm going to get, so let's say f of x is equal to x squared plus 1 now. So I have just a constant here, I don't have any other variable here, but that's not the case here. I have another variable, so I know that f depends on x and y. So if I'm integrating partially with respect to x, my constant of integration is not really a constant, it's going to be a function that now depends on y. So that's what we have just obtained here. So we do know that from what we have done now, f of x comma y is going to be equal to x square, this is cancel this is going to be x square y plus f of y. So the thing now is that we don't know what f of y is going to be, but don't forget that we know that the partial derivative of f with respect to y should be equal to 1 plus x squared, okay, from the equation we started with here. So we are going to keep this. So let's say this is some equation 1, then we will differentiate it now partially with respect to y. If I differentiate it partially with respect to y, I'm going to have this, I'm going to get del f of x comma y del y to be equal to, when I differentiate this partially with respect to y, I'm going to have x squared plus the derivative of my f of y. I don't know what it is, so I will just write it as f prime of y. So I will find out what this is now. So again, I have obtained this derivative by differentiating this. Now don't forget that this derivative itself, we have seen that this should actually be del f of x comma y del y equal to 1 plus x squared. So that means that what we have obtained here should now be equated to what we add here as the coefficient of the y. Don't forget we have said the coefficient of the y is going to be del f of x comma y del y. So now that we have obtained another expression for del f of x comma y del y, it must be equal to the coefficient of the y here, which is 1 plus x squared. So when I equate that, this is equal to 1 plus x squared. So that means from this result, of course, x square, we cancel x square. When I equate this and say this is equivalent to this, so we can compare the like terms. The x square will cancel x square, so that means that our f prime of y will definitely be 1. So we know that f prime of y is equal to 1. So if f prime of y is 1, in this case we have differentiated. This one is derivative partially with respect to y, and this depends only on y, so that's why we could call it f prime directly. That's df dy, because in this case this depends only on y, so it is not some partial derivative. So basically what we have here is simply saying that df, okay, dy is equal to 1. So if that is the case, then f, or say df, is equal to dy. Then we can integrate both sides. So in this case we are integrating this. So this is going to give us f, small f now, is equal to dy. That's 1 dy. That's just going to be y plus the constant of integration, c. So now we are good to go. That means that the f of y that we assumed here, we now know it to be y plus c. So we're going to put that here to get our final expression. So that means that the original function from which this differential equation, this exact differential equation, was derived would be given by x squared y plus our f of y. F of y is now y plus c. So that is that about that. So that means that at the end of the day, our solution is going to look like this. We're going to have this to be some expression that says x squared y plus c is equal to 0. Why? If you take the derivative, so if you now take the differential of this, for instance, let's examine why this is the answer. If you take the differential of this now, that means f of x comma, that means we are saying that let f of x comma y be equal to x squared y plus c equals 0. The differential of this, the f, will now be equal to, that will be del f del y dy plus del f del x dx. And then the differential of this is 0. The differential is going to be equal to 0. So at the end of the day, when I differentiate this partially with respect to y, I'm going to have x squared. This will give me plus 1. Then I'm going to have all of this multiplied by dy plus derivative of this partially with respect to x. That will give me derivative here. That's 2x. Y is a constant. Then the x is equal to 0, which was the equation we started with. So this implicit function that we've just obtained now is the solution of the exact differential equation we are given here. So life can be as easy as that whenever you have exact differential equations. Okay, so let's solve the next problem, then we'll come back to this to see if there's a way we can actually get these results directly without going through all of this. Okay, so let's solve another example. Let me pick one more of them that may be exact. So let's look at the number 3 question here. Number 3 question says that you have x plus sine y dx plus x cos y minus 2y, okay, dy equals 0. So firstly we check if it's an exact differential. So to do that, we differentiate this partially with respect to y, we differentiate this partially with respect to x, and check if they are equal. So if we differentiate this partially with respect to x, so that means, of course, in this case, just to go conventional, this means our m of x comma y is equal to x plus sine y, and our n of x comma y, that's the coefficient of the y, is equal to x cos y minus 2y. So when we differentiate this, del m of x comma y okay, del y is equal to, differentiating this is a constant, so this will be 0. You know what, differentiating partially with respect to y, that means we're keeping x as constant. Then derivative of sine y is going to be cos y. Then here, del n of x comma y del x, that means we're differentiating partially with respect to x, so this is going to be just a constant. Cos y is going to be a constant, so this is going to give us cos y, and this will give us 0. So it is evident that these two are equal, and because of that, the differential equation is exact. So if it is exact, let's now solve it. That means we say that f of x comma y, okay, that's the implicit function now, is the solution. Let this be the solution of the differential equation, such that in our case del f del x, okay, that's f of x comma y del x, is equal to the coefficient, as we did before, of x plus of the coefficient of the x, which is x plus sine y. So from here, we will then proceed to integrate partially with respect to x. So of course, we write out the second one, del f of x comma y del y is equal to the coefficient of the y here, which is x cos y minus 2y. So that is that. Then we will integrate this partially with respect to x, so that's going to give us del f of x comma y, okay, is equal to x plus sine y by cross multiplying here del x. Then we integrate this. So when you integrate this function, it's going to give you back the function f of x comma y is equal to integral of this with respect to x. The first one will give you x squared over 2. The second one will give you minus cos we're integrating this, so this is a constant, sine y is a constant, okay. By integrating partially with respect to x, sine y is a constant, so integrating this, that will give us x squared over 2. Since sine y is a constant, this is just going to give us plus x sine y, so that when you differentiate partially with respect to x, it will give you sine y back. Then plus, as we did before, because we're integrating partially with respect to x, our constant here will be some function that depends on y. So as far as our constant, so to speak, of the integration is concerned, so this is our expression for f of x comma y. But to finalize our results, we need to find out what f of y is, as we did in the previous example. So, and to do that, we already know that the f of x comma y is this. So but if we want to get it from this expression, it will follow that del f of x comma y, okay, del y, yeah, it's partial derivative with respect to y is equal to this. But if we get that from this expression, why are we getting it from this expression? So that we'll be able to equate it to this and then get our f of y from that result. So that is going to give us this. Now when I differentiate this partially with respect to y, this will go off because it does not have any y term. And then differentiating this partially with respect to y will give me, you know, x is a constant now, that will give me x cos y, then plus, then derivative of this partially with respect to y, that will just be the total derivative with respect to y, that will be df dy, that's f prime of y. Since this one depends only on y, okay, so the next thing is I will now equate this result to this result. Of course, usually they will always have something in common like this. So far it is exact, so I will equate this to x cos y minus 2y. So if that is the case, by comparing these two, it is obvious that f prime of y is equal to minus 2y. You know, this x cos x, x cos x, so this one is representing this definitely. So from here, this is a function that depends only on y. This is total derivative of that function, so this is going to be df dy is equal to minus 2y. And from here we conclude that this means the f is equal to minus 2y dy. Then I can integrate this and integrate this, so this is going to give me f, of course, f of y in this case is equal to minus 2y squared over 2. So I believe everybody understands that, how to integrate that. So then plus, some constant of integration c. So of course this will cancel this, so at the end of the day we're going to have f of y is equal to minus y squared plus c. So now we are good to go. So we already know what our function will be, so we'll come back here and put in our f of y. So that means our results will now be our f of x comma y, okay, which is our result. So this should be, let f of x comma y equal to 0 be the solution, okay, be the solution. Alright, so from here f of x comma y is now going to be what we had before. This is x squared over 2 plus x sine y. So I'm going to write that out first. X squared over 2 plus x sine y. So that's the result from here, plus f of y. So we've now found f of y to be minus y squared plus c. So the result, then the final solution is going to be equating this to 0. So at the end of the day, I'm going to have this to be x squared over 2, okay, plus x sine y minus y squared plus c equal to 0. So that will be the solution of the exact differential equation. So that is that about that. So I think this is quite easy and easy stuff to do. So we can also consider something here. So look at something. I told you earlier that what if you are given this in an OBJ question and then you have established that it is an exact differential equation. Once you've established that, then you may not need to go through all of this process. So let's quickly see how we can do that. So let's just see, let's observe what this question was like and what its solution was like. So look at it. The question adds 2xy dx, then 1 plus x square dy. Then at the end of the day, we add this x square y, this is the solution, x square y plus c equals 0. So observe something here, that look at it. If you integrate this coefficient of the x, if you integrate it with respect to x, what will it give you? It will simply give you x squared over 2 times x squared over 2y. Did you get that? When you integrate this, you are keeping y as constant. So when you integrate, that's going to give you, this one is going to give you x squared over 2. That's what we, so this will cancel this. So basically, when you integrate this coefficient of the x partially with respect to x, okay, so it is just going to give you x squared y, okay. So leave it at that. Then look at the next one. If you integrate this partially, of course, with respect to y, it is going to give you y plus x squared y. I hope you got that. When you integrate this now, it's going to give you y plus x squared y. So whenever you do it, whenever it's an exact differential and you do this directly, you're going to have something that they have in common. Yeah. Okay, so just write that expression that they have in common. Write it out only once, because it should appear only once. So that is just x squared y. Then whatever you have left, okay, that is not common to both of them, include it also, plus y. Then include the constant of integration and equate it to 0. So that is how you solve the problem without actually going through all of these processes. So this is the standard process if you are given a theory question, for instance, and it's good for us to actually understand this, because that helps us understand the concepts behind all of this. By doing the same thing, we could also have obtained the solution to this problem directly without going through all of this. So in the same manner, we will look at it now. Look at it. I just want to make a direct comparison to what we did here. So we will, this is the coefficient of the x. We will integrate it partially with respect to x. When you integrate this with respect to x, we are going to have x squared over 2. Integrate this with respect to x, we are going to have x, this is constant now. This is going to be x sine y. So that's it for this part. Then you come here, integrate this partially with respect to y. That will give you something like this. It will give you, with respect to y now, this is going to give you x sine y. It is sine y that has its derivative to be cos y. then this will now be minus, so when you integrate 2y with respect to y, that will be y squared. So when you differentiate minus y squared, it's going to give you minus 2y. So as before, you can identify what is common to them. You always have something that is common to both of them. So x and y, so that's common to both of them. So that one will be written out only once. So write it out only once. That's x sine y. Then every other thing, write them together also. Include every other thing. Then this will be plus x squared over 2 minus y squared, then plus c equal to 0. So that will give us the solution of the differential equation, and that's exactly what we had here when we solved it earlier. X squared over 2 plus x and y, just operating this x and y plus x and y first, so it doesn't make any difference, it's still the same solution. So I hope you got that approach. So let's solve one more question without actually solving. So let's pick the next question here and see if it's going to give us an exact differential. So we had Roman figure 4 here. It's given as y squared dt, okay, plus 2yt plus 1 dy is equal to 0. So in this case, that means this is our coefficient of the t. So in this case, you don't have x and y, but it doesn't make any difference. That means that you're going to get a function that depends on, instead of x now, it will depend on t and y. So just note that change of letter, so it doesn't make any difference, okay? And if you feel confused, you can just change the t to x and then do your solution as before and then change it back, okay? So in this case now, as before, now of course we first check if it's actually an exact differential equation. So how do we do that? You differentiate this coefficient of the t partially with respect to y, it will give you 2y. Differentiate this partially with respect to t, it will also give you 2y. Of course, this is going to give you 0. So of course the two of them are the same, which means that it's actually an exact differential. So there's no need for the long story, leave it at that. So we know it's an exact differential now. So if we want to solve it, how do you solve it? Just integrate this partially with respect to t, that will give you y squared t, okay? That's it for that part. Then for this part, integrate it partially with respect to y, that is going to give you y squared t. I hope you understand that. That's y squared over 2, then this 2 we cancel this 2, then you have t there. So y squared t plus y. Do you get it? So when you integrate this with respect to y to give you y, so we now have what is common to both of them is y squared t. So we're just going to write that only once, y squared t. Then write every other thing left. This is plus y, then include the constants of integration c, then equate it to 0, 0. So that is our solution to this differential equation. So life can be as easy as that without having to go through the entire process. So the remaining questions are like that, and you can solve them in a similar manner. So you can try your hands on those. All right, so I think that is that for that part. So look at the next problem. For instance, look at the number 5. So now we will now consider, finally, before we end this part, we'll now consider a situation where, now what if you are given this kind of equation and then you make your checks and then you find out that the equation is not exact? Does that mean there is no solution? Now there may be a solution yet using this approach. So there are times that you do this, you check your del m of x comma y del y, del n of x comma y del x, and you see that they are not equal. That means that it is not an exact differential equation. So if it is not exact, there could be, I mean possibly, there could be a way for you to actually make it become an exact differential equation. So we're going to consider that situation now. So what you should know about such situations is that Now it depends on the form